This chapter is exploring the idea that every linear transformation has an associated matrix that accomplishes it, and therefore every matrix is associated with a linear transformation. In this section, we're going to determine whether those transformations, they're just functions. They're special functions called linear transformations, but they're just functions, and we can test to see if functions are one-to-one, and we can check to see if those functions are onto. Now, let's remember that we're talking about the domain, right? And our vectors x will live over here in the domain, and we're talking about a codomain, and our vectors y will live over here. And just remember that the range is a subset of the codomain, all right? So because not every linear transformation is onto, sometimes the range is not all of the codomain. All right, so we just have a function t, and it's mapping vectors x, right, from the domain into the codomain. So it's mapping from one set into the other. And when we're using real valued matrices, right, we're just mapping from Rm, right, the number of columns, into Rn. Okay. And again, we said in the last video that that's just because of the matrix operation, right? If I'm going to multiply the matrix A times the vector x, then the matrix A has to have the same number of columns as there are components in x. So therefore, m being the number of columns, right? These vectors that can actually be put into the function, they have to live in Rm. And the thing that will come out because of matrix multiplication are things in Rn. Okay, so now the question is, when is the function one-to-one or onto? And there's a very easy check. We're just going to row reduce and then be able to tell. But let's talk about this. In terms of function notation, we call x the preimage, right? And y is the image. So we're kind of looking at this as x being sort of focused through t, and that's what it's focused on, that image, right? And so one-to-one means that every preimage x has exactly one and only one image y. There's an exact mapping. And x can't, just to be a function, x can't go to two different y's, but we're saying that two different x's can't go to the same y. That's what it means to be one-to-one. What does it mean to be onto in terms of images and preimages? Onto means that for every y in the entire codomain, for every y in the entire codomain, I can find some preimage that gets mapped over to it, right? That's what I mean by onto. Every single thing in the codomain has some image that gets mapped onto it. Now we have a theorem straight from the book. I've just pretty much copy-pasted it over here and reformatted it. So if we want to know about one-to-one matrix transformations, then the following statements are equivalent, right? So if t is one-to-one, then everything on this list has to be true. Also, if any one thing on the list, say 5, is true, then every other thing on the list has to be true. Specifically, t is one-to-one. So any one of these items down here, 4, 5, 6, 7, any of them could be a test to tell whether or not t is one-to-one. So the first thing they put here is basically the definition of what it means to be one-to-one. And it means that if I'm mapping from the image to the preimage, right, that every image, right, this set of matrix equations has at most one solution, right? So we're talking about at most one preimage is what this solution means. Preimage, sorry. And you can tell that here, right? So when I set up the linear system, and I'm going to solve this by row reducing the augmented matrix A comma matrix A comma vector B, right? And the solution is going to be, the solution vector is going to be X. And if we have 1 to 1, then there can only be 1 or 0 solutions, right? Either we have a single solution, that would qualify as 1 to 1, or this thing over in the codomain doesn't have any solutions at all, right? Which again, we've drawn this, right? I have the codomain, but the range may only be a subset of the entire codomain. So that's what it means to be. These are the things we're going to use to verify it. So it's interesting. We have this condition on the null space that identifies whether or not linear transformation can be 1 to 1. And if the null space has only the trivial solution, right, which means the only thing that's in the null space is the 0 vector. If that's true, then we know we have a 1 to 1 function. And that's interesting. An empty null space means that we have 1 to 1 function. Yep, it sure does. And here's the one that we're probably going to use most often. If the columns of A are linearly independent. Okay. And we usually check that by checking to see how many pivots they are. So 5 and 6 are sort of, this is like how we're going to tell. And when that's true, then the range of T has dimension n. What does that mean? Well, remember, we're mapping from Rm, excuse me, from Rn into Rm. And if we're mapping from Rn into Rm, but range T has dimension n, we're mapping from Rn, right, to Rn. It's mapping, I'm sorry, it's mapping to something that has dimension n. That's not quite true to say that. Into something with the dimension equal to n. Which is important, right? Because we'll have this range, excuse me, this codomain. And we're going to be mapping, and it's Rm, be mapping from n to m, right? But whatever is in here has dimension n. So we know that this is 1 to 1, that there is exactly one preimage over here for everything that's in the range. Okay, but again, we're just using 5 and 6 to check this. All right. There's also a theorem for the onto matrices that covers the exact same thing, right? They're all equivalent statements. So we have that T is onto. We have what it means in terms of the transformation and the matrix multiplication. So onto means that anything over here, right, we're mapping from Rn to Rm, right? So Rm is the codomain. Right, Rn is the codomain. And for every B over there, sorry, that should have had a little vector on top. For every B in the codomain, we can find at least one solution. Now this isn't 1 to 1, so we could have multiple. That's fine if we have many solutions, but we have to have at least one. And what does that mean? That means that when I solve this matrix equation, it's consistent all the time, always consistent. Well, again, we're row reducing, right? When we solve this, we're row reducing the augmented matrix AB, and we're checking to see that that is consistent. Also, if the columns of A span Rm, now that's an interesting thing, and that's not what we're going to use to check. Here's what we're going to use to check, option 5, right? Does it have a pivot in every row? So up above, we learned that it's 1 to 1 if it has a pivot at every column. And here we find that it's onto if it has a pivot in every row. So now we'd like to determine if some of these example matrices are one-to-one or onto. So let's take a look at matrix A. It's just a 3 by 3 matrix. And remember, we said that we'll know that it's one-to-one if every column has a pivot, and it's onto if every row has a pivot. So all we need to do to check for one-to-one and onto is to row reduce the matrix. And this is both, right? So with square matrices, as soon as I have a pivot in every column, then I also have a pivot in every row. So we know that A is both one-to-one and onto. All right. Let's look at B. So B is also a square matrix, but notice that it does not have a pivot in every column, nor does it have a pivot in every row. So this is neither. Sorry, I'm struggling with my mouse pad here. There we go. And this will be neither. Sorry, now let's just do the row reduced version of C. So C is a 3 by 5 matrix, and it does have a pivot in every row, but not every column, right? So we have, here's the pivot in row 1, here's the pivot in row 2, here's the pivot in row 3, but obviously it doesn't have a pivot in every column. So C is onto only. It is not one-to-one. And by the way, these what the book calls wide matrices, right, where it has more columns than it has rows, it can only be onto. There's no guarantee that it's onto, right? If we had only had 2 pivots, for example, this wouldn't have been, this transformation would not have been onto. So let me just make the note, this is onto only, and then we will evaluate the last one. We'll take a look at matrix D. Now we have a tall matrix. So your book refers to them as tall and wide, right? So this has more columns than rows. It's a 5 by 3. Now notice that it does have a pivot in every column. Has a pivot in every column, so it's one-to-one. But it doesn't have a pivot in every row, so it's not onto. All right, so this is just a quick demonstration of how to use those 2 theorems about one-to-one and onto. And these are the check steps. We're just going to row reduce the augmented matrix and check to see where the pivots are.